we're doing some reaction classification and balancing. So I have 13 problems for you. I'm going to balance them for you, and then we'll identify what type of reaction each one is. And hopefully you did your homework, so it'll be confirmation of what you've hopefully already done. If not, copy it down if you happen to be one of my students, because I will be checking for it in your binders when I get around to it. Next one shows water, which is likely a gas under the circumstances of this reaction, turning into oxygen and hydrogen. This would be a decomposition reaction. I haven't balanced it yet, so let's do that. The hydrogen is balanced because there's two of them. The oxygen, there's only one on the left, so I can either put a 2 here and double the hydrogen, or I could have put a 1/2 on the O2. Either way, it would have been correct. Number 3. Balance the skeletal equation. I see one person online. Welcome. I didn't see who it was, though. The third equation is iron plus water reacting to form iron oxide and hydrogen gas. This will be a solid, this will be a liquid, this will also be a solid. So is it balanced? No, you need to put a 2 in front of the iron because there's 2 irons over here. And then there's 3 oxygens on the right, so you're going to need 3 oxygens on the left, provided in the form of water, which also generates 6 hydrogens on the left, so you're going to balance that by putting a 3 in front of the H2. And now it's balanced. This is a single displacement reaction. The iron is displacing hydrogen to combine with the oxygen. It's the oxidation of iron. 4, calcium carbonate, which is a solid at room temperature, is forming carbon dioxide, a gas, plus calcium oxide, which will be a solid after the reaction cools off. This is a decomposition reaction. And is it balanced? We have CO2 breaking off from calcium oxide. Yep, it's balanced the way it is. 1 calcium, 3 oxygens, 2 plus 1 is 3 oxygens, and 1 carbon in the form of carbon dioxide there. So that's balanced now. 5. Balance the skeleton equation of sulfuric acid, H2SO4, in aqueous solution, undoubtedly, reacting with solid aluminum to form aluminum sulfate plus hydrogen gas. This is also a single displacement reaction where the aluminum displaces the hydrogen. Let's check for balance. There's 2 aluminums on the right, so we're going to put 2 in front of the aluminum on the left. 3 sulfates, so we're going to have to put a 3 in front of sulfuric acid, and it's going to create 6 hydrogens, so we're going to put a 3 in front of H2, and that's going to balance the 6 hydrogens. So let's double check again. We have 6 hydrogens, 6 hydrogens, 3 sulfates, 3 sulfates, 2 aluminums, 2 aluminums, and that's another single displacement reaction. For single displacement reactions, there's a way of checking to see whether the reaction will happen, because it can sometimes happen that certain metals will not react. under the conditions that you impose on them. And one way of predicting that is, excuse me, it's not COVID, it's my seasonal allergies again. The way you can predict that is by finding out where the metal is on the activity series. And the activity series, I'll teach it to you later, and I'll show you an example specifically when we finish the, but I'll just make a note here. Refer to activity series, because that's how you can predict whether the reaction will happen or not. For example, if you were to put copper with sulfuric acid, it won't work. The reaction won't go, which is why you can use, although I don't recommend it, you can use sulfuric acid to clean your pipes, as long as you don't insist too much, because the copper will not react with the sulfuric acid alone. You'd have to add some other acid, typically nitric acid. If you use nitric acid on copper pipes, you'll destroy your plumbing, because nitric acid will attack copper. So oxygen plus aluminum gives you aluminum oxide. And this is a combination, it's a synthesis reaction. And in the synthesis, you have 2 aluminums on the right, so you're going to have 2 aluminums on the left, 3 oxygens on the right, and 2 on the left. So we'll put a 3 in front of this and a 2 in front of that to get the oxygens balanced, which means we'll have to change the aluminum to 4, and that will balance. So 3, 4, 2, you can't put it in lower terms than that. That's, again, a synthesis reaction. Now let's move us to the other board here. Number 7. Chlorine reacting with potassium bromide. And chlorine is going to be a gas. Potassium bromide is likely going to be in the aqueous state. After the reaction, you're going to have potassium chloride, which will now be in the aqueous state, and you'll have bromine, which will be naturally occurring as a liquid. Probably both of them would be dissolved in the aqueous solution for it to react. This is also a single displacement reaction, but what's happening is you're displacing halogens. And the reactivity is such that the higher up you go on the periodic table, the more reactive it will be and capable of displacing the one below it. So bromine will displace iodine, and chlorine will displace bromine, and fluorine will displace chlorine, because they're higher up on the periodic table on the right hand side. Is this balanced? 2 chlorines on the left, 1 chlorine on the right. No, you have to put a 2 over here. And then the same for the KBr for the same reason, but with bromine as the causative agent. So chlorine, 2 chlorines, 2 potassiums, 2 potassiums, 2 bromines, 2 bromines, balanced. 8. Sodium, which would be a solid under the conditions of this reaction, with chlorine, a gas, normally at room temperature, can react to form sodium chloride, which would turn into a solid as soon as the reaction was over. And you would just have to put a 2 to balance it. This is also a synthesis reaction. Number 9. Balance the skeletal equation of zinc reacting with plumbous nitrate, which would be aqueous under the reaction conditions. And at the end of it, you would get zinc nitrate, which would probably be aqueous because most nitrates are soluble. Anytime you put nitrate with something, it will dissolve in water. Almost all nitrates are soluble, and almost all acetates are soluble. Those two, nitrates and acetates, are the most soluble substances. And then you get lead would be a solid at the end of the reaction. So this is also a single displacement reaction. What happens is the zinc is replacing the lead, and there's a lot of single displacement reactions in this sheet. From now on, single displacement will be symbolized as SD. If you have a double displacement, it will be referred to as DD. 10. NaI, sodium iodide, will be a, that'll be aqueous. And it's going to be reacting with plumbous nitrate. Now, when something is soluble, it's actually more dangerous to living things than something that's not soluble. And case in point, when you go to the doctor for a barium enema, or you can get a barium, you can also drink the barium, and then what they do is they shine x-rays through you, and the barium stops the x-ray. So they can see if you have an ulcer in your stomach by the fact that the barium sulfate, which is insoluble, will coat your intestines. And because it's radio opaque, it blocks the x-rays. So on the parts of your stomach where the barium is sitting, you'll be able to see the outline of your stomach, and if there's an ulcer in your stomach, they'll be able to spot it. So it's one of the ways they use for detecting if you have an ulcer combined with x-rays. Normally, barium is a poisonous metal. If you absorb any barium, it'll kill you. But if you drink barium sulfate, because it's insoluble, you can safely drink it, and none of it will absorb into your body. On the other hand, if you drank barium nitrate or barium acetate, it would dissolve, and you would get ions of barium floating around in your stomach, which would then be absorbed, and that would kill you very quickly. So this little fact of solubility can make all the difference between something being poisonous and not being poisonous. That's why, depending on the solubility of different salts, they may or may not be more or less poisonous to the environment. Very often it's a question of solubilities. Something that's not soluble will just sit there, and even though it could be potentially poisonous, it would be harmless because it doesn't absorb into the organisms, like fish and wildlife and so on. In this reaction, what happens is the two metals will switch places. So the sodium will go with the nitrates and the lead will go with the iodide. The lead and the iodide are insoluble. How do I know that? Well, I have experience, but there are tables you can look up which will tell you the solubility of substances. And typically they'll say something like, if it's soluble, it has more than 1 mole per liter solution is possible. If it's not, when it's considered insoluble, it'll have a solubility of less than 0.1 mole per liter. That's kind of a loose definition, but by and large, that's what they go by. So this is a double displacement. What happens is the metals switch places with the counterions. Nitrate stays in aqueous solution, but the lead and iodide combine to form a precipitate. That's why I wrote solid here. That forms a precipitate. It sinks to the bottom. Forms a yellow precipitate, this reaction. Let's see if it's balanced. I've got 2 sodiums over here. I only got 1 over here, so I'm going to put a 2. And that's going to help me balance with the 2 iodides over here. 1 lead, 2 nitrates, 2 nitrates. So it's balanced, and it's a double displacement. I'm just going to say DD because there's no room. 11. It shows phosphorus, which is likely a solid under these conditions, and O2 gas. They can react to give you diphosphorus trioxide. So I would say put 2 over here to give you the 4 phosphoruses. And then you have 6 oxygens, so you can put a 3 on the oxygen and it'll be balanced. This is a synthesis reaction. Number 12. is ammonium nitrate. Ammonium nitrate goes to water and dinitrogen oxide. That's definitely a decomposition reaction. Now to balance it, we have 2 nitrogens originally, and we still have 2 nitrogens there. 4 hydrogens, so that means we should put a 2 over here to get the 4 hydrogens. And then there's 3 oxygens. We have 2 oxygens there and 1 over there, so that adds up to 3 oxygens. So now it's balanced. I'm going to say this is a solid when the reaction happens, and this is going to be in the form of a gas because you'd have to probably heat it to get those things to happen, to break down like that. And that would be a decomposition reaction. I would not be doing this reaction as an experiment. Ammonium nitrate is explosive, so if you heat it up, it has a tendency to break down violently. In fact, they use it for explosives applications. They typically mix it with something that has a carbon source and then they detonate it. Farmers use it for blasting tree stumps out of the ground, and crazy psychopaths use it for committing terrorist acts. We have silver nitrate reacting with calcium iodide. I'm going to say this is also aqueous, otherwise they won't react. They have to meet in solution. What's going to happen is you're going to get calcium nitrate. You're going to need 2 of the nitrates on that. And most nitrates are aqueous, so I'm going to leave it in aqueous form because it's still going to be soluble. But the silver iodide is definitely not going to be soluble, in my opinion, because most heavy metal salts are not. You're going to have 2 silver iodides, which means you have to have 2 silvers over here, 2 silver nitrates there. Yeah, so let's check it now. Calcium, 1 calcium. 2 iodides, 2 iodides, 2 silvers, 2 silvers, and 2 nitrates, 2 nitrates. It's balanced, and it's a double displacement reaction. That covers the sheet. And I'm going to direct you to go watch my video on single displacement reactions and the activity series. I'll append the video as well. So I'll see you later.